This is the lecture for Part 3 of Section 3.9, Proof by Mathematical Induction. In this video, we're going to discuss strong mathematical induction. Strong mathematical induction is similar to ordinary mathematical induction in that it is used to prove statements of the form for all n p of n, where the domain for the variable n is a set n of positive integers or a subset of n. However, in strong mathematical induction, we strengthen the induction hypothesis. Instead of assuming for the induction hypothesis that p of k is true for one arbitrary positive integer k, we assume that all of p of 1, p of 2, p of 3 on down to p of k are true. The method of proof is based upon the principle of complete induction, so we'll state that here in terms of propositional functions. So suppose p of n is a propositional function with domain the set n of positive integers, and let's suppose 1, p of 1 is true, and 2, for all k in n, p of 1 and p of 2, and all the way down to p of k implies p of k plus 1 is true. Then we can conclude that for all n in n, p of n is true. It's not too hard to see that the principle of math induction implies the principle of complete induction. However, it can also be shown that the principle of complete induction implies the principle of math induction. Therefore, the two principles are logically equivalent. Now, the principle of mathematical induction is sometimes called the weak form to distinguish it from the principle of complete induction, which is often called the strong form. When we use the principle of mathematical induction, the proof is called a weak induction proof. When we use the principle of complete induction, the proof is called a strong induction proof. It's straightforward to modify the procedures outlined earlier for an induction proof of for all n p of n using the principle of mathematical induction to obtain procedures using the principle of complete induction. The procedure for a direct proof is as follows. So first we have the basis step, and for this we need to prove that p of 1 is true. And second, we have the induction step. And this is where things differ. So for the induction step, we need to prove for all k in n, p of 1 and p of 2, all the way down to p of k, implies p of k plus 1 is true. In order to prove this statement, we suppose k is an arbitrary positive integer. We suppose the hypothesis, that is, suppose p of 1, p of 2, all the way down to p of k are all true. And this is the strengthened induction hypothesis. Rather than supposing only that p of k is true, we are supposing that all of p of 1, p of 2, all the way down to p of k are true. We then need to show that the conclusion p of k plus 1 is true. And then using the principle of complete induction, or the PCI, we can then conclude that for all n in n, p of n is true. Now, just as we did for the weak form, we can choose the domain for the strong form to be any set of integers of the form n in n such that n is greater than or equal to n sub 0 for some n0 in n. In this case, for the induction step, we need to show for all k greater than or equal to n sub 0, p of n sub 0 and p of n sub 0 plus 1, and all the way down to p of k implies p of k plus 1. Now, it's not always easy to decide whether to use the weak form or the strong form of mathematical induction when proving a statement. The usual procedure is to try the weak form first. If, when trying to prove the induction step, we find that the hypothesis p of k by itself is not sufficient to enable us to conclude p of k plus 1, then we need to start over using strong induction. So for our first example, let's consider an infinite sequence. A sub n will be the nth term, and we can write that as a1, a2, a3, and so on, defined as follows. So the first term, a sub 1, is equal to 1. The second term, a sub 2, is equal to 3. And then a sub n is equal to a sub n minus 1 plus 2 times a sub n minus 2 for all integers n greater than or equal to 3. So the first two terms of the sequence are specified, and the remaining terms can be computed using the formula for a sub n. For instance, if we substitute n equal 3 into the formula, we obtain a sub 3 is equal to a sub 2 plus 2a sub 1, and a sub 2 was 3, and a sub 1 was 1, so this is 3 plus 2 times 1, which is equal to 5. If we substitute n equal 4 into the formula, we obtain a sub 4 is equal to a sub 3 plus 2 times a sub 2, and we just computed a sub 3 was 5, and a sub 2 was given to us as 3, so this will be 5 plus 2 times 3, which is 11. And then substituting n equal 5, we obtain a sub 5 is a sub 4 plus 2a sub 3, which is 11 plus 2 times 5, which is 21. And continuing like this, we can compute each term in the sequence using the two preceding terms. Now, a sequence a sub n in which the nth term is defined in terms of preceding terms in the sequence is said to be defined recursively. Note that in order to compute the nth term in the sequence using the recursion formula, we need to first compute all the terms one by one up to the n minus first term. We want to prove a formula that allows us to compute the nth term directly without having to compute the preceding terms. And so we want to prove for all n in n, a sub n is given by the formula 2/3 times 2 to the n plus 1/3 times minus 1 to the n. Now, using this formula, we can compute any term in the sequence directly. For instance, for a sub 5, if we substitute n equal 5, the formula tells us that it's equal 2/3 times 2 to the 5th plus 1/3 times minus 1 to the 5th, which is 2/3 times 32 plus 1/3 times minus 1, 64/3 minus 1/3, which is 63/3, which is 21. And that matches the result that we computed earlier. Now, to prove this result, well, first note that it has symbolic form for all n in n p of n, where p of n is the propositional function a sub n equals 2/3 times 2 to the n plus 1/3 times minus 1 to the n. So this is the formula we're trying to prove. So we don't want to denote the recursion formula by p of n. So p of n is the formula for a sub n that we're looking to compute. So for our proof, we're going to use strong mathematical induction on n, and we'll explain later why we need to use strong induction in this example. So first we have the basis step, and for this we need to show that p of 1 is true, and substituting n equal 1 into the expression for p of n, we obtain p of 1 is the formula a sub 1 equals 2/3 times 2 to the 1 plus 1/3 times minus 1 to the 1. And the expression on the right side of p of 1 is 2/3 times 2 to the 1 plus 1/3 times minus 1 to the 1. This will be 2/3 times 2 is 4/3 minus 1/3, which is 1. Now, since a sub 1 was given to us as 1, then the left side equals the right side, so p of 1 is true. So this proves the basis step. Next, we have the induction step. And for this, we need to show for all k in n, p of 1 and p of 2, all the way down to p of k, implies p of k plus 1. So we suppose k is an arbitrary positive integer. We suppose p of 1, p of 2, down to p of k are all true. And we need to show p of k plus 1. And this will be a sub k plus 1 equals 2/3 times 2 to the k plus 1 plus 1/3 times minus 1 to the k plus 1. So to prove this, we're going to consider the following cases. K equal 1 will be our first case, and k greater than or equal to 2 will be our second case. Now, at this point in the proof, it's not clear why we need to consider these two cases, but as we go through the proof, we'll see why these are necessary. So case 1, we're going to suppose that k is equal to 1, then k plus 1 is equal to 2, and so we need to show p of k plus 1, which in this case is p of 2, which will be the formula a sub 2 equals 2/3 times 2 squared plus 1/3 times minus 1 squared. Now, the expression on the right side of p of 2 is 2/3 times 2 squared plus 1/3 times minus 1 squared, and this will be 8/3 plus 1/3, which is 9/3, which is 3. Now, since a sub 2 is 3 was given to us, then the left side equals the right side, so p of 2 is true. And this proves case 1. For case 2, we're going to suppose that k is greater than or equal to 2, and we need to show p of k plus 1, which is the formula a sub k plus 1 is 2/3 times 2 to the k plus 1 plus 1/3 times minus 1 to the k plus 1. Now, in this case, since k is greater than or equal to 2, then k plus 1 is greater than or equal to 3. And the recursive definition of the sequence tells us that a sub k plus 1 equals a sub k plus 2 times a sub k minus 1. That's obtained by replacing n with k plus 1 in the recursive definition. Now, if you recall, in the statement of the example, the recursive definition held for n greater than or equal to 3. In this case, k plus 1 is greater than or equal to 3, so we can use this definition. Now, from the induction hypothesis, both p of k and p of k minus 1 are true. So p of k gives us a formula for a sub k, and p of k minus 1 gives us a formula for a sub k minus 1. So we can substitute for a sub k and a sub k minus 1 in the recursive definition for a sub k plus 1, and we obtain a sub k plus 1 was a sub k plus 2 times a sub k minus 1, and then this will be the expression shown. So this is obtained by substituting the formula for a sub k and substituting the formula for a sub k minus 1 from the induction hypothesis. Okay, now we want to simplify the right-hand side to show that we obtained the formula for a sub k plus 1 in the propositional function p of k plus 1. So this is going to take several steps. So we can first distribute the 2 in the third and the fourth terms. And then if we rearrange the order of the terms so that we have swap the second and third terms. And so the third term now has a 2 times 2/3 times 2 to the k minus 1. And so we can group that factor of 2 with the 2 to the k minus 1, and we'll end up with 2/3 times 2 to the k. And so now the first two terms are identical, 2/3 times 2 to the k. So that will be 2/3 times 2 times 2 to the k. And we can factor a 1/3 out of the third and fourth terms. And then in the first term, 2 times 2 to the k is 2 to the k plus 1. And in the second and third terms, we can factor out minus 1 to the k minus 1. And taking it out of the second term, we're left with a minus 1. And factoring that out of the third term, we're left with 2. And then minus 1 plus 2 is obviously just 1. And we're going to rewrite the 1 as minus 1 squared. And the motivation for doing this is we want to group it with the minus 1 to the k minus 1 power. And so then minus 1 to the k minus 1 times minus 1 squared will give us minus 1 to the k plus 1. So now we've shown that a sub k plus 1 is 2/3 times 2 to the k plus 1 plus 1/3 times minus 1 to the k plus 1. Well, this is exactly the formula we are trying to prove in p of k plus 1. So this proves p of k plus 1 in this case. And this completes the proof of the induction step. We've proved both cases. And since we've proved the basis and induction steps, then by the principle of complete induction, for all n and n, p of n is true. Now, this is obviously a complicated proof, and so here are a few comments concerning some of its details. First, why did we need to use strong induction rather than weak induction? That is, why did we need to use the principle of complete induction instead of the principle of mathematical induction? Note that in case 2 of the induction step, we needed to use both p of k and p of k minus 1 in order to prove p of k plus 1. If we had been using weak induction, we would have assumed only p of k was true and would not have been able to use p of k minus 1. Second, why did we need to introduce the two cases in the proof of the induction step? Well, in order to prove p of k plus 1 in the induction step, we needed to use the recursion formula. So that was the formula a sub n is a sub n minus 1 plus 2a sub n minus 2, and we used it with the case n equal k plus 1. Now, according to the definition of the sequence, this formula applies when n is greater than or equal to 3. So we can only use this formula when k plus 1 was greater than or equal to 3, or k is greater than or equal to 2. But since we had supposed k was an arbitrary integer greater than or equal to 1 in the induction step, we needed to prove the case k equal 1 separately. Now, one of the most famous examples of a recursively defined sequence is the Fibonacci sequence. So let's take a look at this sequence in the next example. So the Fibonacci sequence, which is denoted f sub n, and so this is again an infinite sequence, f1, f2, f3, and so on, is defined by f sub 1, the first term, is 1, f sub 2, the second term, is 1, and f sub n is f sub n minus 1 plus f sub n minus 2 for all integers n greater than or equal to 3. For instance, for n equal 3, we obtain f sub 3 is f sub 2 plus f sub 1, which is 1 plus 1, which is 2. And then f sub 4 will be f sub 3 plus f sub 2, which is 2 plus 1, or 3. F sub 5 is f sub 4 plus f sub 3, which is 3 plus 2, or 5. F sub 6 is f sub 5 plus f sub 4, which is 5 plus 3, or 8. And the terms, we can continue in this way. The terms in the Fibonacci sequence are called the Fibonacci numbers. And this sequence is named after the 13th century Italian mathematician Leonardo Fibonacci, considered one of the greatest Western mathematicians of the Middle Ages. Now, as in the previous example, in order to compute the nth Fibonacci number, the nth term in the sequence, using the recursion formula, we need to first compute all the Fibonacci numbers one by one up to the n-first number. So using the following formula, however, we can compute the nth Fibonacci number directly. So we want to prove this in this example, that for all n and n, the nth Fibonacci number f sub n is equal to 1 over square root of 5, 1 plus square root of 5 over 2 to the nth power, minus 1 over square root of 5 times 1 minus square root of 5 over 2 to the nth power. So this formula looks like the formula in the previous example, but the numbers are obviously much more complicated. Now, to prove this, well, first note this has symbolic form for all n and n p of n, where p of n is the propositional function, which is the formula for f sub n. Now, to shorten the amount of writing we'll need to do in this example, let's let phi be 1 plus square root of 5 over 2, and phi bar is 1 minus square root of 5 over 2. We can then write the propositional function as f sub n is 1 over square root of 5 times phi to the nth power minus phi bar to the nth power. The number phi is called the golden ratio, while the number phi bar is called the golden ratio conjugate, or sometimes it's called the silver ratio. So for our proof, well, we're going to use strong mathematical induction on n, and we start with our basis step, and we need to show that p of 1 is true. So substituting n equal 1 into the expression for p of n, we obtain p of 1 is the formula f sub 1 is 1 over square root of 5 times phi to the 1 minus phi bar to the 1. Now the expression on the right side of p of 1 is 1 over square root of 5 phi to the 1 minus phi bar to the 1. And substituting for phi and phi bar, this is 1 over square root of 5 times 1 plus square root of 5 over 2 minus 1 minus square root of 5 over 2. And we can combine these two fractions. The square root of 5 terms will cancel, and we're left with 1 over square root of 5 times 2 square root of 5 in the numerator over 2 in the denominator. And the 2's cancel, the square root of 5's cancel, and we're left with just 1. Now, since f sub 1 is equal to 1, then the left side equals the right side, so p of 1 is true. And this proves the basis step. Next, for the induction step, we need to show for all k and n, p of 1 and p of 2, all the way down to p of k, implies p of k plus 1. So we'll suppose k is an arbitrary positive integer. We'll suppose p of 1, p of 2, p of 3, all the way down to p of k are all true. And we need to show p of k plus 1. And this is the formula for f sub k plus 1, which says that it's equal to 1 over square root of 5 phi to the k plus 1 power minus phi bar to the k plus 1 power. Now, as in the previous example, we'll consider the following cases, k equal 1 and k greater than or equal to 2. So for case 1, let's suppose k equals 1. Then k plus 1 is equal to 2, so we need to show p of k plus 1 will be p of 2, and this is f sub 2 is 1 over square root of 5 phi squared minus phi bar squared. So the expression on the right side of p of 2 is 1 over square root of 5 phi squared minus phi bar squared, and substituting for phi and phi bar, this will be 1 plus square root of 5 over 2 squared minus 1 minus square root of 5 over 2 squared. And squaring these out, we obtain this expression. And now these two fractions both have the same denominator, so we can combine the numerators, and you can see that the 1 terms and the 5 terms will all cancel, and the 2 square root of 5 terms will combine to give us 4 square root of 5 over 4. And the 4's cancel, the square root of 5's cancel, and we're left with 1. And since f sub 2 is equal to 1, then the left side of P of 2 equals the right side, so P of 2 is true, and this proves case 1. So for case 2, we're going to suppose k is greater than or equal to 2, and we need to show P of k plus 1, which is f sub k plus 1 is 1 over square root of 5, phi to the k plus 1 minus phi bar to the k plus 1. In this case, since k is greater than or equal to 2, then k plus 1 is greater than or equal to 3, and the recursive definition implies that f sub k plus 1 equals f sub k plus f sub k minus 1. So again, the recursive definition only holds for n greater than or equal to 3, and so here our so we can apply the recursive definition with n replaced by k plus 1. And from the induction hypothesis, both P of k and P of k minus 1 are true. So P of k gives us a formula for f sub k, and P of k minus 1 gives us a formula for f sub k minus 1, and we can substitute both of these into the expression for f sub k plus 1. So doing the substitution, we obtain f sub k plus 1 is f sub k plus f sub k minus 1, and this will be the expression shown. And now we can factor out a 1 over square root of 5 from all of these terms. And then we can rearrange the order of the terms in the brackets, so switch the second and the third terms to put the phi powers together and the phi bar powers together. And then we can factor out a phi to the k minus 1 from the first two terms and a phi bar to the k minus 1 from the third and fourth terms. Okay, now we want to simplify this, and so we're going to examine phi squared. So phi squared is 1 plus square root of 5 over 2 squared. And so this is 1 plus 2 square root of 5 plus 5 all over 4. And this will be 6 plus 2 square root of 5, which we can factor a 2 out of to give us 2 times the quantity 3 plus square root of 5 over 4. And cancel the 2 with the factor of 2 in the denominator. We obtain 3 plus square root of 5 over 2. And 3 can be broken up into 2 plus 1. And 2 over 2 will just give us a 1, and we're left with 1 plus square root of 5 over 2. Now 1 plus square root of 5 over 2 is just phi, so this is 1 plus phi. So these calculations show that phi squared is equal to 1 plus phi. And similarly, it can be shown that phi bar squared is 1 plus phi bar. So in our expression for f sub k plus 1, we have a phi plus 1 factor and a phi bar plus 1 factor, and so we can replace the phi plus 1 with phi squared and replace the phi bar plus 1 with phi bar squared, and then phi to the k minus 1 times phi squared will give us phi to the k plus 1, and phi bar to the k minus 1 times phi bar squared will give us phi bar to the k plus 1. And so we obtain f sub k plus 1 equals 1 over square root of 5 phi to the k plus 1 minus phi bar to the k plus 1. And this is what we're trying to show for P of k plus 1. So this proves P of k plus 1 in this case. And so this completes the proof of the induction step. And since we've proved the basis and induction steps, then by the principle of complete induction, for all n, P of n is true. Now for another example, a little different from the first two, let's suppose we have a large supply of 3 cents and 5 cent postage stamps. What postage amounts can we make using just these denominations of stamps? For instance, we can obtain an amount of 8 cents using 1 3-cent stamp and 1 5-cent stamp, or an amount of 9 cents using 3 3-cent stamps. However, there's no way to obtain, for instance, an amount of 7 cents. So we want to prove that we can obtain any amount greater than or equal to 8 cents using 3-cent and 5-cent stamps. To prove this, we can first formulate the problem as follows. Let's let A be the number of 3-cent stamps and B be the number of 5-cent stamps. Then the total postage amount is 3A plus 5B. And we can obtain an amount of n cents provided that n is equal to 3A plus 5B for some non-negative integers A and B. The problem then becomes, for each integer n greater than or equal to 8, there exist non-negative integers a and b such that n is equal to 3a plus 5b. And so we can write this in symbolic form as for all n greater than or equal to 8, p of n, where p of n is the propositional function, there exists an a, there exists a b, such that n is equal to 3a plus 5b, where the domain for a and b is the set of non-negative integers. So for our proof, we're going to use strong mathematical induction on n, starting at n sub 0 is equal to 8. So for our basis step, we need to show that p of 8 is true. And for n equal 8, the propositional function will be there exists an a and a b such that 8 equals 3a plus 5b. Well, we can just choose a equal 1 and b equal 1. Then a and b are non-negative integers, and 8 is equal to 3 times 1 plus 5 times 1. So this proves that p of 8 is true, which proves the basis step. Next, for our induction step, we need to show for all k greater than or equal to 8, p of 8 and p of 9 all the way down to p of k implies p of k plus 1. So since we're starting our induction at n sub 0 is equal to 8, our hypothesis also starts with p of 8. So suppose k is an arbitrary integer greater than or equal to 8, and suppose our hypothesis p of 8, p of 9, all the way down to p of k are all true, and we need to show p of k plus 1, which will be there exists an a, there exists a b, such that k plus 1 equals 3a plus 5b. So let's consider the cases k equals 8, k equals 9, and k is greater than or equal to 10. Now, while it may not be clear at this point in the proof why we need to consider these cases, it will become clear as we go through the proof. So for case 1, we're going to suppose that k is equal to 8. Then k plus 1 is equal to 9, so we need to show p of k plus 1, or p of 9, which will be there exists an a and a b, such that 9 equals 3a plus 5b. Well, we can just choose a equals 3 and b equals 0. Then a and b are non-negative integers, and 9 is equal to 3 times 3 plus 5 times 0. So this proves that p of 9 is true, which proves case 1. For case 2, we're going to suppose that k is equal to 9, then k plus 1 is equal to 10, so we need to show p of 10, which is there exists an a and a b, such that 10 is equal to 3a plus 5b. So we'll choose a equals 0 and b is equal to 2. Then a and b are non-negative integers, and 10 is equal to 3 times 0 plus 5 times 2. So this proves that p of 10 is true, which proves case 2. So then case 3, we're going to suppose that k is greater than or equal to 10. So we need to show p of k plus 1, which again is there exists an a and a b such that k plus 1 equals 3a plus 5b. So this is an existential statement, so we'll set it up as we usually do for existential statements with our two columns. So in the left-hand column, we need to find an a and a b, and in the right-hand column, we'll verify that a and b satisfy our two conditions. The domain, a and b are supposed to be non-negative integers, and our propositional function is that k plus 1 equals 3a plus 5b. Now, note that k plus 1 is equal to k minus 2 plus 3. Now, since k is greater than or equal to 10 in this case, then k minus 2 is greater than or equal to 8. So by the induction hypothesis, p of k minus 2 is true. So if you go back, for our induction hypothesis, we supposed p of 8, p of 9, all the way up to p of k are true. And since k minus 2 is greater than or equal to 8, then k minus 2 will be included in the numbers between 8 and k. So p minus k is assumed to be true. And this means that there exist non-negative integers a prime and b prime such that k minus 2 is equal to 3a prime plus 5b prime. And so then k plus 1, as we said earlier, is k minus 2 plus 3, and this will be 3a prime plus 5b prime plus 3, which is equal to 3 times the quantity a prime plus 1 plus 5b prime. And so this looks like our propositional function. And so this tells us what to choose for our a and a b. So we'll choose a to be a prime plus 1 and b to be b prime. So we've now found our a and a b. And so now we need to verify that they satisfy our two conditions. So since a prime and b prime are non-negative integers, then a equal a prime plus 1 and b equal b prime are also non-negative integers. And from the work on the left, we know that k plus 1 equals 3 times the quantity a prime plus 1 plus 5b prime, and this is 3a plus 5b. So our domain is satisfied and our propositional function holds. So this proves our existential statement. So this proves p of k plus 1 is true, which proves case 3. And this completes the proof of the induction step. And since we've proved the basis and induction steps, then by the principle of complete induction, for all n greater than or equal to 8, p of n is true. So in this proof, we again needed to use strong induction. In case 3 of the induction step, we needed to assume p of k minus 2 was true in order to prove p of k plus 1. So using only weak induction, the induction hypothesis p of k would not have been sufficient to prove p of k plus 1. Also in this proof, we again needed to consider cases in the induction step. So in the general case, in case 3, we needed to use p of k minus 2 in order to prove p of k plus 1. But to ensure that p of k minus 2 was true, we needed k minus 2 to be greater than or equal to 8. So we needed to suppose that k is greater than or equal to 10. Since we had supposed that k was an arbitrary integer greater than or equal to 8, we needed to prove the cases k equal 8 and k equal 9 separately, so this resulted in the 3 cases. So for one more example, which requires strong mathematical induction, we're going to first review some definitions. So a natural number p greater than 1 is prime, provided that the only positive integers of p are 1 and itself. So therefore, p is prime, provided that for all positive integers r and s, if p is equal to r times s, then r is equal to 1 or s is equal to 1. So this is saying that if p has a divisor r or s, then those divisors, well, if p has a divisor r, then r has to be 1 or p, and the other divisor s has to be 1 or p. So in symbolic form, p is prime, provided that for all r and s and n, p equals r times s implies r equals 1 or s equals 1. Now a natural number n greater than 1 is composite, provided that it is not prime. So therefore n is composite provided the negation of the previous condition holds, which will be there exists an r in s and n such that n equals r times s, and r is not equal to 1 and s is not equal to 1. So a natural number n is composite provided that there exist positive integers r and s such that n equals r times s and r is not equal to 1 and s is not equal to 1. And note that in this case, since r and s are positive integers, then r has to be strictly greater than 1 and s has to be strictly greater than 1. And since s is strictly greater than 1, then r has to be strictly less than n. And since r is greater than 1, then s will have to be strictly less than n. So both r and s are greater than 1 and less than n. Now the integer 1 is neither prime nor composite, so it's in its own category. Now we'll also need to apply the following result, which we've proved previously in an example. So this is for all integers a, b, and c with a not equal to 0 and b not equal to 0, if a divides b and b divides c, then a divides c. So this means that the divisibility relation is transitive. Okay, we're now ready to state our example, and this is to prove every integer n greater than or equal to 2 is divisible by a prime number. That is, for every integer n greater than or equal to 2, there exists a prime number p such that p divides n. So this has symbolic form for all n greater than or equal to 2, q of n, where q of n is the propositional function, there exists a prime p such that p divides n. So this is where the domain for p is the set of prime numbers. Now we're using q of n for the propositional function in this example rather than p of n, since we're using p for the prime number in the propositional function. So we're going to use strong mathematical induction on n, starting at n sub 0 is equal to 2. And so for the basis step, we need to show that Q of 2 is true. And substituting n equal 2 into the expression for Q of n, we obtain Q of 2 is the statement there exists a prime p such that p divides 2. So we need to show there exists a prime p such that p divides 2 in order to show that Q of 2 is true. Well, since 2 is itself a prime and 2 divides 2, then Q of 2 is true. So this proves the basis step. For the induction step, we need to show for all k greater than or equal to 2, Q of 2 and Q of 3, all the way down to Q of k, implies Q of k plus 1. So we'll suppose k is an arbitrary positive integer greater than or equal to 2. We'll suppose our hypothesis, Q of 2, Q of 3, all the way down to Q of k, are all true. And we need to show Q of k plus 1, which will be there exists a p such that p divides k plus 1. That is, we need to show there exists a prime number p such that p divides k plus 1. So we're going to consider the following two cases. K plus 1 is prime is our first case, and k plus 1 is not prime in our second case. So we're introducing our own cases here, and since these cases are exhaustive, k plus 1 is either prime or not prime, then this is a valid way to introduce cases. So for case 1, we're going to suppose that k plus 1 is prime, and we need to show Q of k plus 1, there exists a p such that p divides k plus 1. Well, this is an existential statement, so to prove it, we can go ahead and set it up as our standard existential proof with our two columns. And so in our left-hand column, we need to find a prime p, and in the right-hand column, we need to verify that p satisfies our domain condition and our propositional function. So in this case, we need to find a prime p that divides k plus 1. Well, since k plus 1 is a prime, and k plus 1 divides itself, then we can choose p equals k plus 1. So that gives us a p, and by the hypothesis in this case, p equal k plus 1 is a prime, so this satisfies our domain condition. And since k plus 1 divides itself, then p divides k plus 1. So the propositional function holds. So this proves the existential statement, which proves Q of k plus 1 in this case. So for case 2, we're going to suppose that k plus 1 is not a prime, and we again need to show Q of k plus 1, there exists a p such that p divides k plus 1. As in case 1, this is an existential statement, so we'll set up our two columns again. So we need to find a p and then verify p satisfies the domain and propositional function. Now, since k plus 1 is not a prime number in this case, then k plus 1 is composite. And this means there exist integers r and s such that k plus 1 equals r times s, and both r and s are greater than 1 and less than k plus 1. Now, since 1 is less than r is less than k plus 1, then r is actually greater than or equal to 2 and less than or equal to k. Since r is an integer, being greater than 1 tells us that it's actually greater than or equal to 2, and being less than k plus 1 tells us that it's actually less than or equal to k. And the induction hypothesis then implies that Q of r is true. So the induction hypothesis was that Q of 2, Q of 3, all the way up to Q of k are true. So whatever r is, it's greater than or equal to 2 and less than or equal to k, so it's going to be included. So Q of r will be included in the list of statements that are true in the induction hypothesis. And this means that there exists a prime p such that p divides r. So we're going to choose this prime p. So we've now found a prime p, and we want to verify that it satisfies our conditions, and by assumption p is a prime. And since k plus 1 is equal to r times s, where s is an integer, then r divides k plus 1. And since p divides r, and r divides k plus 1, then by the transitive property of the divides relation, p divides k plus 1. So this proves the propositional function. Okay, so this proves the existential statement, which proves Q of k plus 1 in case 2. And since we've proved both cases, this completes the proof of the induction step. And since we've now proved the basis and induction steps, then by the principle of complete induction, this proves for all n greater than or equal to 2, Q of n. Now, why did we need to use strong induction in this proof rather than weak induction? In the proof of case 2 of the induction step, when we had k plus 1 equals r times s, we needed to apply the induction hypothesis to r. That is, we needed to know that Q of r, which is there exists a p such that p divides r, was true. If we had known that r is equal to k, then the induction hypothesis obtained using weak induction would suffice, because then we'd be supposing that Q of k, or Q of r, was true. However, we only knew that r was greater than 1 and less than k plus 1, which is equivalent to r is greater than or equal to 2 and less than or equal to k. So we didn't know that r was equal to k. We only knew that it was greater than or equal to 2 and less than or equal to k. And so we needed the induction hypothesis provided by a strong induction proof. We also used cases in the proof of the induction step in this last example. In the second case, since k plus 1 was supposed to be composite, we were able to write it as the product of two smaller integers, r and s. And we were then able to apply the induction hypothesis to r.